Well, welcome to this session, which is the presentation from the awardee for the Krumbein Medal. This would normally be read or introduced by the nominator, Graham Bonham Carter, but he is not here, so you'll have to put up with me instead. So to introduce John, Professor Emmanuel John Carranza is the 34th winner of the William Christian Krumbein Medal of the institution of the IAMG. This medal is the highest honour bestowed by our association, and it's been awarded every year from 1976 to 1996 and every second year thereafter. John was recognised for each of the three criteria for the award of this medal: distinguished research, service to IAMG, and service to the profession. John earned his BSc in geology in 1983 at Adamson University in Manila, the Philippines. He then spent 18 years working for the Mines and Geosciences Bureau in Legazpi City, Philippines. And for the next 15 years, he taught and completed his graduate work at the International Institute for Aerospace Survey and Earth Sciences in the Netherlands, where he completed his PhD in GIS-based mineral potential mapping in 2002. After spending several years as university faculty in the Netherlands, Australia, and Brazil, he finally settled in South Africa, and he's now a professor of economic geology at the University of the Free State in Bloemfontein. It's notable that although John started publishing rather late in his career, more than once he has an extraordinary productive in a relatively short period of time. In the last 20 years, he has published more than 215 papers in peer-reviewed publications and has written an important and sole-authored textbook entitled Geochemical Anomaly and Mineral Prospectivity Mapping in GIS. His journal papers have been cited, according to Google Scholar, 15,400 times, and he has an H index of 69. John's most noteworthy service to the IAMG has been as Editor-in-Chief of Natural Resources Research. In this journal, he's put it on the map since he took over in 2013. After many years of trying, the journal was finally added to the Science Citation Index in 2017. Remarkably, over only 4 years, the ISI index reached 5.146 for 2020. This is an astonishing achievement in such a short period of time. The number of issues of NRR per year has increased from 4 to 6, and a total of 220 papers were accepted for publication in 2020. Those papers were cited, on average, 5 times in the first 2 years after publication, which is very strong evidence of both popularity and quality. Besides his stellar work with NRR, John has been on the editorial board of Computers and Geosciences since 2009 and has guest edited a special issue of that journal. He has organized and convened sessions at several IAMG conferences. John has been very active with other professional organizations. He is a senior associate editor of Geochemistry, Exploration, Environment and Analysis, and he is an associate editor of Ore Geology Reviews and the Journal of Geochemical Exploration. He has organized specialized sessions in conferences of the Geochemical Society, the European Association of Geochemistry, the Society for Geology Applied to Mineral Deposits, and the Association of Applied Geochemists. He has carried out collaborative and supportive projects with several national geological surveys and given courses for the International Atomic Energy Agency. John has supervised the thesis work of 31 master's students and 12 PhD students at last count. In short, John Carranza has made an important contribution in the application of mathematics in the earth sciences, and by his distinguished research, his service for the IAMG, and his service to the profession. So I welcome John to deliver this year's Krumbein Medal oration.
Thank you very much, Peter. And yeah, I thank the IAMG first because I had no plans to come to IAMG 2022 at the start of the year. But that changed when I got the email from the president of IAMG, Peter Dow, that I was chosen to be given this year's Krumbein medal. And so I have to make a schedule, change in my schedule of teaching. So last week and this week, I have to give my students the test so I can escape from teaching. Because I'm teaching three subjects, and I couldn't escape if I didn't do that. So, and well, I did not tell my students that I was coming here. Otherwise, they would not wish me luck. Anyway, so wow, that's the title of my talk. Hopefully, this will be a representative of the medal that I'm receiving. Otherwise, I won't. I think Peter will not give it to me. Okay. So first of all, let me thank every one of those who have led to this award and to this presentation. Okay. First, I would just like to thank the Lord for all the blessings that He has given me all these years. And, well, I cannot do nothing without His blessings. So secondly, I would like to thank Graham Bonham Carter, who unfortunately is not here. So as Peter said, he nominated me for this award. And, well, I haven't seen Graham for a long time. And I miss my Chinese friends, especially Ren Guang. He was the one actually who asked Graham to nominate me for this award. So Ren Guang, if you're watching over there via Zoom, thank you. And of course, I want to thank the IAMG Awards Committee for deciding to give me this award. I thank my friends in Brazil, my friend Carlos Roberto and Paulo Miguel, not only for friendship, but for the research collaboration, especially the work that will be presented here. So this presentation is derived from these three papers. The first one at the top was published in Economic Geology, the second one in Ore Geology Reviews, and the third one in Scientific Reports. Of course, we have to thank those who give us money to do research. First one is FAPESP. This is an agency in São Paulo in Brazil, for giving scholarship to Paulo Miguel, and to CNPq for giving me and Beto and I money for research. And of course to Vale, who allowed us to do research in their property in the Carranza Penal Province. And we really thank him because at one time when we were doing research, we were at the bottom of the pit at 1 o'clock in the afternoon. And for those of you who knows about open pit mining, 1 o'clock is blasting time. So we were there at the bottom of the pit. So the field geologists, the mine geologists called the mining engineer, we're still here at the bottom of the pit. And so for the love of science, give us about 15 minutes more. Okay, so here we go. Okay, so the basis of this presentation is that we know, or by research, that mineral deposits are fractal in nature. That means they preserve or they exhibit scale invariance of their geometric properties at different scales. And most of the early work on this field is on a regional scale with little, on a local scale. And well, most mineral deposits or certain types of mineralization are showing fractal properties because the host structures also are fractals, as you can see in this slide. So here you have faults, which you can see are showing self-similarity at different scales, SC structures also, as well as breccias. So in this research, we hypothesized that the regional scale controls of mineral deposits can be inferred from regional scale and to microscopic scales. We added the microscopic scale because this work has not done before. And we started at the regional scale because most exploration work starts on a regional scale and then narrowing down to the local scale. And so, because it's difficult to cover a lot of ground at the start, so if you can start at the local scale or even to the microscopic scale and then upscale that interpretation, that should help mineral exploration. So how did we do this approach, our work? We investigated the geometry of mineralization at different scales, regional, local, and microscopic. We evaluated the structural control at each of these scales, and then we compared and contrasted our interpretations at these different scales. We did the research using the IOCG deposit in Carranza. IOCG meaning iron oxide copper gold. So this is a good deposit. It's really structurally controlled. And we chose the Susego because this is a world-class deposit, meaning it has been studied quite a lot. And so we can control our interpretations based on the spatial analysis. And if we can repeat the approach that we do. Okay, just schematically, this slide shows the approach. You can see there are different maps of different scales. The solid arrows represent our downscaling of the data that we collect. So we start from a regional scale, moving down to local scale, where we also do mapping of structures. Then we collect samples at that scale, and we prepare thin sections. We do microfracture structural mapping on a thin section scale. And then we look at the distribution of ore minerals at a microscopic scale. And then the dashed arrows represent the upscaling of information or interpretation from the micro to the thin section to the local and to the regional scale. And we do that to prove our hypothesis. Okay, so this is the study area in Carajás, over on the other side of the Atlantic. That's Brazil. And the study area is in the state of Pará. That's the Carajás Mineral Province. This is a very old geological terrain, underlain mainly by Archean rocks. So mainly Archean rocks. And the deposits are hosted in the metamorphosed volcano sedimentary units of Nearchean age. The heat sources of these deposits are the granites and the mafic, ultramafic rocks. Before this deposit was formed, there was a sinistral transpression at 2.6 billion years ago, just before the close of Neo-Archean. So Neo-Archean ends at 2.5 giga. So about 100 million years, we have this transpression, which resulted in the structural makeup of this terrain, and which also controlled the mineralization at that time. So in a mineral system concept, we all have the four components here. We have source controls, the heat source, the fluid source. We have the transport, the pathways, as well as traps. Okay, that's what we know about the Carajás. So we first move on to the regional scale. These are just the data that we used. We digitized from literature the locations of IOCG deposits represented there as dots, as well as the structural geology as lines. So on a regional scale, mineral deposits are depicted as points. So suitably, we have to use methods which allow for analysis of points in space. So we use fractal analysis, Frey analysis, and we also supported that with spatial association analysis, but I'm not going to show results here about the spatial association analysis. We use different kinds of methods because they give different information, which when we compile them, gives us more robust interpretation. Okay, so we start with a set of points representing the IOCG deposits. We did back counting to measure the scale and the geometry. But fractal analysis does not give us the trends, so we did Frye analysis. Okay, just very quickly, what is back counting Frye analysis? On a set of points which represent a certain process, in this case, mineralization, on top of that, we put a grid of different sizes indicated by the small delta D, and we count the number of bucks which contain at least 1 point, and then we plot the data on a log-log scale. On a X, we have the delta D. And then we fit this data with lines. Because it's log-log, then we have power law equations. The powers are the fractal dimensions. So very simple, very straightforward. So these are the results for an original scale. We can see that the log-log plot can be fitted by 3 straight line segments, separated by inflection points at 15 and 40 kilometers. And these 3 lines depict 3 fractal dimensions. At a scale of less than 15, we have 0.19. At a scale of 15 to 40, we have a fractal dimension of 50. And the scale of more than 40 kilometers, a fractal dimension of 1.48. So what do this mean? Okay, based on what we know of Euclidean geometry, we can say, or we can infer, that the pattern of points represented by the IOCG at a scale of less than 15 kilometers, they behave like points, meaning at that scale they cluster, which is typical of deposits. So they cluster at certain places. And at a scale of more than 40 kilometers, this pattern of points behave like lines, which means that the clusters are disposed along a linear trend, or linear trends. And in between 1540, they behave between these 2 objects. It's the behavior, but they are not points, they are not lines, it's just the behavior. Okay. So now we go to Frye analysis, because fractal analysis does not give us trends. We want to know the trends. So what is Frye analysis? This was proposed in 1975 by a fellow named Frye. He's a metamorphic geologist. He looked at metamorphic grains under the microscope, and he used this, or proposed this method. So what does it do? Okay, here's a set of points. Each of these points is used as a center for translation. So you can pick any one of them at random, but using all of them. So we can start with this one circle in red, and then we put an XY axis as the reference, and then we choose another point and bring the whole set of points on top of that. And then we repeat that procedure until all the points has been used as a center for translation. So what it does, it repeats the patterns depending on the number of points in the set. And if you have n number of points, you will get n squared minus n Frye points. So it repeats the pattern so many times that you're able to depict the trends that these points show or exhibit, or which is not obvious in the original set of points. So with this set of Frye points, we can do directional analysis. We can create Rose diagrams for all pairs of Frye points, or for Frye points at a certain distance from each other. So we do that because we want to play with the scale and see what trends we have at different scales. The question is, at what scale? At what distance? For that, we can answer that with point pattern analysis by finding the shortest distance between 2 points, which has the maximum probability. In this work, we did not use this. We simply use the distance indicated to us by the fractal analysis. We decided to use fractal analysis because we have 3 breakpoints. Instead, if we do the point pattern analysis, we will only have 1 breakpoint. Okay, so there you go. You have the 5 points there on the left. And we can do all sorts of interpretation for this. Firstly, we outline the field of 5 points using the outermost points, and we can see a sigmoidal feature. And within this feature, we can draw lines which can be discerned from the pattern of points. And surprisingly, this, our interpretation coincide with the known structural geology. Because of that transpression, we have the sigmoidal shape. And then actually, this object here, which is also a sigmoid, is a dilational jog, which is favorable for the focusing of fluids. That's where you have mineral deposits there. And you can see that jog also conceptually within the cloud of 5 points. Okay, so that was the 2.6 giga sinistral transpression, which caused that sigmoidal shape of the Carranza mineral province. Okay, so now we go to the trends depicted by the Frey analysis. We look at all points, only pairs of 5 points within 40 kilometers, and only pairs of 5 points within 15 kilometers. And we can see a lot of consistency across these different scales. And of course, we have some major difference when we use all pairs of 5 points. That means the scale of structural controls differ when you change the scale of observation. Okay, so just for visual interpretation, we put the red lines, the major axes, the blue lines as the minor axes of these trends. Okay, just a repetition of the interpretation of the fractal analysis. As we have mentioned, the pattern of IOCG in Carranza, they behave as points on a small scale. They behave like lines on a larger scale. And we can see that also in the structural geology map. We can see lots of linear features, and the deposits are located at certain positions depending on the structural geology. Okay, so now we change scale from regional to local. Okay, so this is the Carranza. We zoom in a bit, and now we're looking at the ore bodies at Sossego. There are different names of these ore bodies within the Sossego deposit. This deposit, the ore body is called Pista, that's Siqueirino, that's Bayano, it's Coral, and Sossego. They give different names to different parts of the ore bodies because they were different at different, they were discovered at different times. Okay, what data do we have on a local scale? We have a geological map, we have a structural map, we did measurements in the field, and we have a map of IOCG ore bodies. All of this courtesy of the mine, except for the measurements that we did in the field. Okay, these are the samples that we collected. We collected oriented samples at certain locations where we have structural measurements. Those in red are structural data, and at 27 of those 51 sites, we also collected oriented samples. And as you can see, some of them are at the bottom of the pit. Now, when we look at the data as a whole, we saw a boring one trend, west-northwest, south-southeast. And it doesn't match what we see in the geology. Yeah. The geology is more complicated, but when we look at all the structural data, we see a very boring one trend. So that's not correct. So what we did, we studied the geology in detail, the lithology as well as the structural geology, and then finally we decided to divide the area into 3 domains. Domain 1 in blue, domain 2 in red, and domain 3 in green. And when we start plotting the strike of the structures versus their location, we can see differences within these 3 domains. So that was our basis for our analysis of the data, these 3 different domains. Okay, then we look at the trends based on our structural measurement from map faults. So we can see domain 1 and domain 3 more or less showing the same trend, and domain 2 showing different trend. Why is that? Because domain 2 is the youngest domain in this area. This is directly related to that 2.6 giga sinistral transpression. And domain 2 and 3 were just reactivated and affected, not in the same way as domain 2. Okay, at the bottom, we see these are modeled faults. These are faults modeled by the mine geologist from drill holes. So these are not surface faults. That's why we see different trends from map faults in domain 1 and modeled faults. That means at the surface of domain 1, or surfaces of domain 1 and 2, there's a change in strike of the structures. So there's some rotation. But domain 2, it stays the same because that's the youngest domain. Okay, now we switch scale again from local to microscopic. We use our hand lens. No, we use a microscope. This is a photomicrograph. There you can see some chalcopyrite and some magnetite. Okay, so the ore mineralogy of the deposit is mainly chalcopyrite, so we studied chalcopyrite. What did we do with the oriented thin samples? We cut all our samples, oriented samples, in the horizontal. Why is that? Because all structural measurements that you see on the map are all based on the horizontal. Yeah. So what we see on a thin section, which is oriented, we can compare what we see on a regional or local scale map. And we digitized all our thin sections and using ArcGIS, and you can see it's digitized in a millimeter scale to centimeter scale. Okay, so we did a lot of different analyses from thin section. So starting at the bottom there, in one section, thin section, we looked at 3 different sites representative of what we see from the whole thin section. We took microphotographs, and then we did some image analysis of these photographs. Particularly, we created a binary map of chalcopyrite on a microscale. And then from that binary map, we did point pattern analysis using centroids of each grain. We did fractal box counting, fractal radial density, phi analysis. We also did fractal box counting on those polygons represented by the grains, and as well as shape analysis. Lots of very exciting work. Okay, now we just don't analyze those grains. We have to go back to geology. What does geology tell us? We have to look at the ore textures, because different ore textures reflect different processes. If we don't, then we are mixing everything. So based on the classification of ore textures by Taylor, we were able to classify our ores into disseminated, sparse, or infill. Yeah. The disseminated and the sparse represent alteration, and the infill are like vein fillings. So first, what we did was to check whether those grains are random in space. So we did some point pattern analysis. We compared the expected mean distance to the observed mean distance. And the white line there, the diagonal line, represented the references by which we can say whether it's random or not. So anything above is non-random. Anything within that, along that line, will be random. So our main conclusion, those ore grains are not random. If they're not random, something controlled them. Okay, we looked at the fractal dimensions, the fractal properties. Here is just we're plotting the R squared, or this is the line of fit on the log-log plot. And then we can see that there's a good line of fit, good fit, indicating that we have fractal properties exhibited by those chalcopyrite grains in the thin sections. Okay, now we look at fractal dimensions. If we look at all grains, all images, we have a median of about 1.5, and yeah, it doesn't say much. It's very boring. So we applied the ore texture classification. Then we see differences. We see that the disseminated grains have higher fractal dimension compared to the sparse and the infill textures. So we can see that the fractal dimensions vary substantially, and well, we expect these results because the spatial patterns represent different ore components with different textures, different processes. And what we can say is that the behavior of the fractal dimension is partly explained by the geometric variation of the chalcopyrite grains in terms of abundance, area, and homogeneity. Homogeneity in terms of distribution in space, not in the ore minerals, because these only represent chalcopyrite. Okay, then we look more closely whether the distribution is bifractal or monofractal. Only a few of them showed monofractality. Most of the samples that we had exhibited bifractality. And still we can see differences in the three different ore textures. BP there at the bottom is the breakpoint in the log-log plot. And so also we can see that there's bifractality even in the micro scale. Okay, then we go to Frye analysis at the micro scale. So the blue colors there represent all grains. The gray clouds surrounding it are only Frye points within a radius of less than 800 microns. And we see similarity between all grains and only certain grains within a distance of 800 microns from each other. Now, what does this mean? Now, if we look at, when we looked at different structures in the area, we noticed that the pattern shown by these alteration components, the sparse and the displacement, they display different orientations as the ductile structures. So that means these sparse and disseminated ore textures were controlled by ductile structures. On the other hand, when we look at the infill, they exhibited similar trends as the brittle structures. So the infill ore textures were controlled by brittle textures. So indeed, different ore textures represent different processes. Okay, we go to the shape analysis. Here we plot the minor axis and the major axis. For each grain, we use the ellipse fit program to fit an ellipse to each of the grain, and then that gives us data about the long and short axis, and we plot them against each other. And we can see that regardless of the ore textures, they exhibit more or less the same anisotropy. So they are elongated, which means they're all structurally controlled. Okay. So this is just a summary of what we have seen at the micro scale, and all these rows diagrams are from analysis. We show here those in red, the major axes, the blue arrows are minor axes. Now, how do we make sense of that, what we see at the micro scale? To make sense of that, we went back to the local scale, so we're now upscaling. We also fit ellipses on the ore bodies on a local scale. So the trends that we see on a micro scale, we see back on a local scale in the ore bodies. So from mineral grains to ore bodies, we see the same trends, orientations. So what we have seen so far, the spatial distribution of the ore grains is predominantly non-random, but mostly fractal. The shape of the grains is predominantly anisotropic. There, they show fractal geometry. They have well-defined directional patterns, and they are consistent with local scale. The distribution and shape show considerable variation, which is a function of their abundance, their size, and degree of clustering, all due to structural controls. And they're predominantly bifractal, indicating or suggesting that more than one fractal process was involved in the formation of ore in this region. And that's because fluid flow is fractal. Okay, just summarizing different scales, orientations at different scales. Here we put what we have seen from a micro scale. So what we can see on a micro scale, we see on a local scale, we also see on a regional scale. The variations, of course, only is related to the strength of the rocks. Yeah, you can never see a clear-cut fracture. It's always jagged. But on a micro scale, you see the orientation of those jaggedness. So comparing the micro scale trends, here also different domains, we compare them to local scale and on a regional scale. So everything we see on a micro scale, we see on a local to regional scale. So, is our hypothesis correct or not? Anyway, so the fractal property of IOCG deposits in Carranza indicate systematic patterns in their geometry, and they remain independent of spatial scale, even when we consider the complexity of the geology as well as the metallogeny of the area. Microscale patterns of ore minerals show geometric relations which are consistent with regional as well as local structures. And it seems possible, well, we have to be stronger than that. It is possible to extract useful information from microscopic to local scales to infer regional structural controls of mineralization. And so fractal geometry is a useful tool in regional scale mineral exploration. Okay, we have to do more work. Actually, from Brazil, I applied this methodology when I went to South Africa in a poorly explored region and a very different style of mineralization. There we have shear zone hosted gold, but the style of fracturing is reverse faulting, so thrusting. So we have mostly shears instead of brittle fractures. Different style, but we see, we have more or less the same conclusions. So what's the exploration significance? When we explore a new area, we know the geology, or we know the structural geology, but we don't know anything about mineralization. So we go to the field, we look for indications of mineralization. That's what mineral exploration is about. And let's assume we find one outcrop there in yellow. So we go to that area, we make measurements around it, So that's your local scale. We collect oriented samples, and we follow the whole approach. So we can look at ore minerals at the microscale, and we should be able to answer the question, which sets original scale structures are controls of mineralization in this region. And therefore, by knowing that, we know which predictor to use in mineral prospectivity mapping. And with that, I thank again the Lord for helping me establish the work in my hands. And for that, I thank you all.
Thank you, John. Any questions from the audience?
On a local scale.
Hello.
Yeah.
I don't know if you can hear me from this position, because there is a problem, the echoing the chamber. Okay. First, I think it's quite counterintuitive, your results for the infill data, because it's quite obvious that infill image has a dimension 2. What do you think when you compare the images, okay, with your results for the fractal dimension? I remember that the infill is quite obvious that it's 2, but I think the fractal dimension was the smallest from the 3 types of images you have. I'm not a geologist, so I cannot.
Is this one?
Yes, I cannot use the concept of your field, okay? But you have 3 images, okay? So infill ore, it's quite. I'm quite sure that it's almost 2 the dimension, and the first, yes, almost 2 the dimension, and the first one between 1 and 2. It's quite clear, but I think in your other, I think it's in the previous slide, you show that the fractal dimension of the infill ore is less than the fractal dimension of the disseminated. Is that right?
Okay, so
yeah, so blue is larger than red is larger than blue. Yeah. It's quite counterintuitive for me.
Yeah, the green and the blue are almost the same. The green and blue are more or less the same. Yeah. Yeah, red and blue are really different. Wow. Well, that's the results that we have. We cannot change the results. I don't know if that means anything. I don't know. Genetically, I don't know.
Other questions? Yeah, Peter?
John, many of these IACG-type deposits also have another characteristic. It's preferentially deporting to grain size with grade. Has that happened here as well? So when you crush the material, the grade preferentially deports to certain fraction sizes? Okay. I was wondering then whether that was also a fractal relationship.
Well, when we looked at the thin sections, we did not see any effect from cutting. Maybe the diamond saw that was used was really hard. Or it cannot be harder than 10 anyway.
Other questions? Again? Okay. No one seemed to move?
I don't know if it's a question or a suggestion, but how can you evaluate the confidence level of your fractal dimensions? For example, one thing that people in some fields that I already worked with since 20 years ago saw that they should use surrogate data to test the confidence of the fractal dimension. For example, random shuffling of your own data and then evaluate the fractal dimension again. If that's not possible, generate a random distribution and test your method on that random distribution. Okay, then you can see the confidence level of the fractal dimensions that we have. Okay, are you trying something like that or not yet?
Okay, so you are suggesting we simulate a fractal pattern of fractal dust, and we compare.
Sorry to interrupt. Do we have other questions? If not, I guess it's time for the coffee break. Thanks a lot, John.
Thank you.
Oh, sorry. Oh, one important thing, yes. The official award ceremony for the Krumbein medal.
We can't let John go without some evidence that he's actually been awarded the prize. So, firstly, a certificate recognising your award, and something you can keep for your grandchildren, a nice, big, heavy medal. Wow. Congratulations.
Thank you. Now I have to test this for